Hello, this is Keta Kusagawa from NTT Social Informatics Laboratories. Today, I want to talk about the Boneh-Katz transformation revisited. Shoot random oblivious sample PKE from lattices and cos and its application. Let's start. So this is a summary of our talk. On the right-hand side, we presented the Ganeti-Halevi transformations, which is proposed in 2004. The Ganeti-Halevi transformations converts weakly secure TBE into the strongly secure PKE, into CC secure PKE. Later, so the Boneh-Katz the Boneh and Katz propose the modified version of the Ganeti-Halevi Katz transformation. So they propose conversion from tag-based encryption into the PKE. So the difference between them is the attached primitives. The Ganeti-Halevi Katz transformation uses one-time signature, but the Boneh-Katz transformation uses mark and weak commitment. And so they both of them convert weakly secure TBE with their chosen primitives into CC secure PKE scheme. So today, we examine the shoot randomness. That is, we found that the Boneh-Katz transformation can preserve shoot randomness of the underlying primitives into the primitives. So that is, if we use the shoot random TBE and shoot random mark and shoot random weak commitments, then the Boneh-Katz transformation converts them into a shoot random secure PKE. But unfortunately, so the Ganeti-Halevi Katz transformation failed to preserve shoot randomness. So that is, even if we use the shoot random TBE and the shoot random one-time signature, we cannot construct the shoot random CC secure PKE by using the Ganeti-Halevi Katz transformations. So this is what I want to talk about in this talk. So we in this talk we first review TBE and mark PKE and mark and weak commitment. Then so we next review the why Ganeti-Halevi Katz transformation failed to preserve the shoot randomness. Then we talk about why Boneh-Katz transformation can preserve shoot randomness, and we finally talk about instantiation and its applications. Okay. Let's start. The first one is the preliminaries. Okay. We will first review the public key encryption, PKE in short. So PKE consists of three algorithms: GEN, which is a key generation algorithm, and ENC and DEC. On input the security parameter 1 to the k, the key generation algorithm output encryption key EK and decryption key DK. And on input EK and M message, encryption algorithms output the ciphertext CT. And the decryption algorithm takes DK and ciphertext as input. Its output message M or the rejection symbol both. So we say that PKE is a shoot random CC secure if any efficient adversary cannot win the game defined as false. Okay, the adversary first receives this EK from the challenger. Then so it can use decryption oracle freely. So that is if the adversary can send ciphertext, this one, and it can receive this message or rejection symbol both. In the challenge phase, the adversary sends a message M. The challenger generates CT0 star as an encryption of this message M. And the challenger generates CT1 star as a random ciphertext chosen from this ciphertext space CT. Then so it sends CT0 or CT1 star, like as this one. Then the adversary again can use the decryption oracle freely. But if it sends CT star, then so it will receive this port. Then so the adversary will output B prime as its guess of the challenger hidden bit, this B. So we say that the adversary wins if this B prime is equal to B. And if the adversary can't guess this B, then we say that public key encryption is pseudo-random CCA secure. Next, we talk about tag-based encryption. So we use this subscription T to denote the algorithms belong to the tag-based encryption. The key generation algorithms output the EK and DK as a public key encryption. And the next, so, the encryption algorithms takes this tag additionally. So this is called as tag. So the encryption algorithm takes EK and this tag and the message M. It output ciphertext C. The decryption algorithm takes DK and the tag and the ciphertext. It output message or bot. So we say that tag TBE is PR STWCC secure. So here, so PR means pseudo-random, and ST means selective tag, and WCC means weakly pseudo-ciphertext attack. If the adversary cannot win the following game. In this game, so the adversary first declare this tag, tau star. So receiving tau star, the challenger sends EK to the adversary. The adversary can use decryption oracle freely. So it sends tau and C to the decryption oracle. But in this game, so if tau is this declared tau star, the adversary will receive spot. In the challenge phase, so the challenger sends message M to the challenger. The challenger generates C0 star as an encryption of message, and then the selective tag tau star. And it also generates C1 star as a random ciphertext from ciphertext space this board C. And then so the challenger sends C0 star or C1 star. The adversary again can use decryption oracle freely, but again, so if tau is tau star, then it will receive spot. The adversary finally outputs its guess B prime, and we say that the adversary wins this game if B prime is B. So if the adversary wins with probability greater than half, so sorry. If the adversary's winning probability is very close to half, then so we say that tag-based encryption is PRSTWCC secure. Okay, so we next review weak commitment. So here, so weak commitment means the string in to be committed is randomly chosen. So weak commitment consists of two algorithms: send algorithms and reconstruct algorithm. On input security parameter, this send algorithms output R, which is the string to be committed, and commitment information com, and decommitment information dec. And reconstruct algorithms takes commitment and decommitment as input. It output string R or rejection symbol bot. Okay. So we require weak commitment to be hiding. So here, so hiding means that the real string R and commit is computationally indistinguishable randomly chosen R props and commitment. And we say that we commitment is binding if it is hard to find R prime and commitment and decommitment prime, which is valid one from real R and commitment and decommit generated by send. We also require we commitment to be pseudo random. So here pseudo random means that this commitment is computationally indistinguishable from random string commitment plus. And we additionally require that non-invertibility. So this is a weaker than binding. So this requires that it is hard to find the valid decommitment information for random string commitment plus. So this is the review of weak commitment. We next talk about a message authentication code, MAC. So MAC consists of two algorithms, tag and verify. So tag takes R as key and mu as a message, and it outputs sigma as a MAC tag. And the verification algorithms takes R as secret key and mu as a message and sigma as a MAC tag, and it outputs true symbol or false symbol, both. Okay, we require MAC to be SEUF1 OTCMA secure. So here this means that stringly existential unforgettable under the one-time choose message attacks. So in this setting, the adversary sends this mu at once. Mu once. And receiving on this mu, the challenger chooses R randomly, and it produces this sigma correctly. Then send sigma to the challenger, to the adversary. So adversary outputs mu star and sigma star, and this adversary wins if this mu star and sigma star is valid one, and this mu star and sigma star is not equal to the mu and sigma. So if any exchange adversary cannot win this game, so we say that MAC is SEUF1 OTCMA secure. And we additionally require that this MAC to be pseudo random. So here pseudo random means that so correctly generated this MAC tag is computationally indistinguishable from random strings this sigma plus if if R is hidden. So this is a review of MAC. Okay, we next talk about Boneh-Katz transformation. Okay, so let us review Boneh-Katz transformation, so CHK in short. So in the original paper, so CHK proposed the conversion from IBE to PKE, but we here use the conversion from TBE to PKE. So this is generalized by Kiltz in 2006. So in the CHK transformation, the public key encryption's key generation algorithm is the same as tag-based encryption's key generation algorithms. So in so to encrypt message with encryption key, so it first generates one-time signature verification key (OVK) and one-time signature signing key (OSK) here. Then it encrypts message with tag-based encryption with tag. Here, so we set OVK as tag. Then this is ciphertext. Okay. Then finally, so we produce this sigma as a one-time signature of C under the OSK. Then we set ciphertext as OVK and sigma C and sigma. So in decryption, so we first pass CT as a tuple OVK and C and sigma. Then so we first decrypt C into message by using the OVK as tag. So if this M is bot, then it outputs bot. And if this verification pass is not passed, that is, this sigma is invalid, then the decryption algorithms outputs both. So otherwise, so that this means that the message is correctly decrypted and the signature is valid, then the decryption algorithms output this message M. So this is a fat CSK conversion. This internally. Okay, so let us try to CSK preserves pseudo randomness on efficiently sample explainable domain. Okay, let me introduce ESE domain review. So the domain D is efficiently samplable and explainable if it has two algorithms, SAMP and XProof. So this SAMP means sampling algorithms, and XProof means explain algorithm. Okay, so let us assume that this X is sampled by this randomness row, and this explain algorithms takes X as input and it output row. So here the key point is explain algorithm samples this row randomly such that X conditioned on X is equal to SAMP algorithms with randomness row. So therefore, so if we have X, then we can produce explain the randomness row which samples X correctly. Okay, so this is what ESE domain says. Okay, so let us try to the CSK conversion preserves pseudo randomness on ESE domains. So in order to do so, so we first assume the ciphertext or tag-based encryption is pseudo random. Okay, so this is very reasonable one. And we next assume that the OVK one-time signature verification key is pseudo random. Okay, this is also reasonable. But so if we consider the sigma, so we can verify the signature. And we don't know how we can explain the randomness of OVK with sigma. So if we consider the ESE domains. The wrapping up, so the problems is the ciphertext of CSK, OVK, C, and sigma is verifiably sparse. So intuitively speaking, so this should those ciphertexts should involve some secret information which cannot be explainable. But the Boneh-Katz transformation helps us. Okay, let us review Boneh-Katz transformation. So as CSK transformations, Boneh-Katz transformation use the same key generation algorithms as the tag-based encryption algorithms. Tag-based encryption's key generation algorithms. So to encrypt message under this EK, so it first generates R and commitment and decommitment by using commitment sending algorithm. Then it generates ciphertext C of a message and decommitment under the tag commitment. Then it produces the MAC tag sigma using the R as secret key on the the message ciphertext. Then it outputs CT as commitment and C and sigma. So in decommitment, we first pass CT as a commitment and C and sigma. So by using the decryption algorithm of TBE, we obtain a message and decommitment. And if they are both, then the decryption algorithm output both. So otherwise, we reconstruct R from this commitment and decommitment. And if this R is both, then the decryption algorithm outputs both. And we verify MAC tag. And if this verification is not passed, then the decryption algorithm outputs both. So otherwise, it outputs message as plain text. Okay, so fortunately, so this Boneh-Katz transformation may be okay. Let's check our intuition. Okay, so let us try to prove this ciphertext is a pseudorandom on the ESE domain. Okay, so let us assume that this ciphertext C is pseudorandom. So this is reasonable one. And assume this commitment and sigma is pseudorandom. And this is okay. Good. And in the case of CSK transformation, we can verify a signature of ciphertext. But in the Boneh-Katz transformation, we cannot verify this MAC tag sigma. So the point is commitment of C and sigma ciphertext is publicly unverifiable. So this allows us to prove Boneh-Katz transformation preserves pseudo-randomness. So we omit the details of the proofs, so please see the full paper. Okay. So we next how we instantiate tag-based encryption and recommitment and MAC and its applications. So we can construct pseudo-random PRSTWCCS TB schemes as follows. From lattices, we can use the CSKP10, ABB10, MP12, and BBDQ18, and so on. And fortunately, so the ciphertext space is ZQ to L for some L. So therefore, those ciphertext space is efficiently sampleable and explainable domain. In the case of calls, so we can use those rate words 1 and dot rate words 1 and the case massively Peter-Zack ones and U and Chan's TBE. So we additionally prove the following two, the last two schemes are pseudo-random. And their ciphertext space is F2 to L. So that is a L-bit string. So apparently, the L-bit string space is efficiently sampleable and explainable domain. So therefore, we obtain PRSTWCC TBA schemes from lattices and calls. And we can construct the recommitment and MAC as follows. So fortunately, so the Boneh-Katz proposed the recommitment, and those recommitments satisfy our requirements. And MAC case, so we can have a one-time secure ones, very well-known one-time secure one, also satisfy our requirements using like collision resistant hash function and the universally bound and pairwise independent hash function. This is pseudo-random, and recommitment, the left-hand side and recommitment, and the right-hand side MAC fortunately, so pseudo-random. Finally, so we'll review our applications. So for example, so combined with trapdoor commitment, we can construct universally composable non-interactive bit commitment from PRCC secured PKE with efficient ESE domain. And simulation-based selective opening CCA secure PKE by combining the information theoretically secure code and hash. And we also have anonymous CAN-based AKE, AKEs. Okay, so let us wrap up. So this is a summary of our slide. So we propose a PRCC PK from tag-based encryption. So roughly speaking, so using the Boneh-Katz transformation, we can construct PRCC PK from PRTB. And we can instantiate such a PRTB from calls and lattices. So this is a very interesting ones. The other applications, we can construct bit commitment and simulation-based selective opening CCS PKE and anonymous AKEs. So finally, so as a concurrent work, so Kitagawa, Masuda, and Tanaka also propose a PRCC PKE from PRCP PKE plus key dependent message CCA secure DEMS. Okay, that's all. Thank you.